Hello friends, welcome to the video lecture series on digital image processing. I am Dr. Dafda, and in this 73rd video class of DIP, we will study object recognition based on decision theoretic methods and matching for digital image processing and its implementation in MATLAB. In our previous video class, we studied pattern and pattern classes where we learned that object recognition can be done using decision theoretic methods or structural methods, and in this video class we will learn decision theoretic methods. Starting with the name, decision theoretic methods means taking the decision theoretically. That means we take the decisions or discrimination on a particular pattern and do the object recognition. And matching means we match our pattern with some known prototype pattern. Okay, so let us start. This is the slide that we studied in our previous video class. In object recognition, automatically the things are identified from the picture, and we know that it can be done using two methods: decision theoretic methods, which is also called quantitative descriptor, which we are learning currently, and the other method is the structural method. See, the basic concept in decision theoretic methods is the idea of pattern matching based on measures of distance between pattern vectors, where it includes decision or discriminant functions and decision boundaries. Let x is equal to x1, x2 up to xn transpose represent a pattern vector, and say this x is a iris flower. Then for w pattern classes, that is omega 1, omega 2 up to omega w, the basic problem is to find w decision functions d1 of x, d2 of x up to dw of x with the property that if x belongs to class omega I, di of x is greater than dj of x for j is equal to 1, 2 up to w, where j is not equal to I. So this iris versicolor is omega I and iris setosa is omega j. Okay, so we are matching this x with omega I and omega j, that is di of x and dj of x. So if di of x is greater than dj of x, that is omega I matching is greater than omega j matching, then x belong to class omega I. Okay, that means the iris flower belongs to iris versicolor. Okay, and unknown pattern x is said to belong to the ith pattern class if upon substitution of x into all decision functions, di of x yields the largest numerical value. And say we want to classify x, which is a pattern, and we are given a finite set of classes of objects, and we want to categorize the pattern x into one of these classes. So to do so, we apply x to all decision functions and categorize x to the class of best fit. So here this iris flower x is matching or fitting into iris versicolor omega 1 or omega I, and hence we make the decision that this flower x is a iris versicolor flower. Okay, now other point to remember is the decision boundary separating class omega I from class omega j is given by the values of x, for which di of x is equal to dj of x, or we can say that dij of x is equal to dix minus djx, which is equal to 0. So this will be the decision boundary separating omega I from omega j. So if x belongs to class omega I, then obviously dij of x will be greater than 0. That is, di of x will be greater than dj of x, and if the class belongs to omega j, then we will get a negative value, that is dij of x is less than 0, dj of x is greater than di of x. Okay, the decision theoretic methods are of three types: matching, optimum statistical classifier, and neural networks. In matching, an unknown pattern is assigned to the class to which it is closest with respect to a metric. This can be done using minimum distance classifier, which we'll be just studying in detail. It computes the Euclidean distance between the unknown pattern and each of the prototype vectors. And other technique in matching is correlation, where it can be directly formulated in terms of images, or correlations can be established. The second type of decision theoretic method is the optimum statistical classifier, which is a probabilistic approach to recognition. And the third type of decision theoretic method is the neural networks, where, as the name suggests, a non-linear computing elements, which are called neurons, are organized in the networks, just like the neurons are arranged in our brain to take different decisions. Okay, let us now understand matching and minimum distance classifier. Matching is an important concept in computer vision and object recognition. Images of the same item can be taken with any angle and any lighting condition and any scale for matching, and the simplest approach of matching is the minimum distance classifier. Matching represents each class by a prototype pattern vector, and the prototype of each pattern class is the mean vector given by this equation. So for say this pattern class of iris versicolor flower, this is the mean vector, and for iris setosa, this is the mean vector, which is shown using dark square and dark circle respectively. Now, using the Euclidean distance as the measure of closeness, the distance dj of x is given by this equation. So this equation means that say the distance between this mean vector and this square, that is given by dj of x, and we assign x to class wj if dj of x is the smallest distance. That is, the smallest distance implies the best match in this formulation. So if this distance is smallest, it is the best match for this particular pattern class, and it is easy to show that selecting the smallest distance is equivalent to evaluating the function given by this equation and assigning x to class wj if dj of x yields the largest numerical value, as we just understood earlier. If x belongs to class wi, di of x is greater than dj of x. So this is based on the largest numerical value. So this formulation agrees with the concept of decision function. Now suppose these are two pattern classes, iris versicolor given by squares and iris setosa given by circles, and the decision boundary between this class omega I and omega j is given by, so this equation comes from here. Okay, now for di of x we can write the equation from this equation. In place of j we replace I, so that will be di of x, and we will replace dj of x from this equation. In simplifying, we will obtain this equation, and we know that the decision boundary equation should be equal to 0. So this equation is equal to 0. So the surface given by above equation is the perpendicular bisector of the line segment joining mi and mj. So this is mi, this is mj, and this is the perpendicular bisector. For n is equal to 2, here we have n is equal to 2, that is versicolor and setosa. The perpendicular bisector is a line, as we can see here. For n is equal to 3, it is a plane, and for n greater than 3, it is a hyperplane. The two classes, iris versicolor and iris setosa, are denoted by omega 1 and omega 2 respectively. So this is omega 1, this is omega 2. And these have sample mean vectors m1 is equal to 4.3, 1.3 transpose. So we can see here this is our m1, which is 4.3 and 1.3, and m2 is equal to 1.5, 0.3 transpose. So this is our m2, that is 1.5 and 0.3. Now using this equation we can write d1 of x and d2 of x for these m1 and m2 like this as d1 of x and d2 of x, and now we know that the decision boundary equation is given by d12 of x, which is equal to d1 of x minus d2 of x. So this is our d1 of x minus d2 of x. We obtain the equation like this, which is equal to 0. So this comes out to be 2x1 plus 1.0x2 minus 8.9. So this is that line, the perpendicular bisector line. Now substitution of any pattern vector from class omega 1 would yield d12 of x greater than 0. Why? Because it belongs to omega 1. And conversely, any pattern from class omega 2 would yield d12 of x less than 0 because it belongs to omega 2. In other words, given an unknown pattern belonging to one of these two classes, the sign of d12 of x, that is, if d12 of x is positive, it belongs to omega 1, and if it is negative, it belongs to omega 2, would be sufficient to determine pattern's class membership. I hope it is clear. In practice, the classifier works well when the distance between means is large compared to the spread of each class, which is rarely the case. This occurs seldom unless the system designer controls the nature of the input. So normally the classes are overlapping, and we have to design the system in such a way that the distance between the means is large. An example is the recognition of characters on bank checks, American Bankers Association E13B font character set. So this is E13B font character set, and we can see that the characters are purposely designed on a 9x7 matrix to facilitate easy reading. Also the characters are stylized to maximize the difference between them. So the characters are styled in such a way that there is difference in between each character and overlapping is very less or minimum. The font was designed to be readable by humans, but the overriding purpose was that the characters should be readable by the machines quickly and with high accuracy. That means the overlapping should be as minimum as possible, and that we can see using the signature waveforms, and the signature waveform of each character is different. And from our video lecture number 67 on signatures, so we know that when the signature waveform is different, each character or each object will be identified uniquely. Okay, so this is how the minimum distance classifier works. Let us implement the minimum distance classifier and matching in MATLAB. The Google Drive link to download the PPTs or class notes is given in the description box. Also, you can find the MATLAB code in the description box. That is all for this video class. Thank you very much.